To simplify a complicated electrical circuit, we use the principle of symmetry. When a circuit is symmetrical about a line, that is, two parts of the circuit are mirror images of each other, then the potential and current also be symmetrical. We will discuss two types of symmetry, that is folding symmetry and mirror symmetry. Let us first discuss about folding symmetry. Here a circuit is given. We can easily analyze the circuit and calculate the effective resistance between points A and B by using the Wheatstone bridge principle. But we will do this using folding symmetry. So, as we are told to calculate the effective resistance between point A and B, we will draw a line through these 2 points and we'll check if the circuit is symmetrical about this line. Let we replace this resistance of value R by 2 resistance, each of value R by 2 in series connection. That is, if we take 2 resistance, each of value R by 2 in series, then the equivalent resistance will be equal to R. So we replace this resistance R by 2 resistor, each of value R by 2 in series combination between C and D, so that we can easily check the symmetry of the circuit. So if we draw a line through point A and B, we can see that the circuit is symmetrical about this line, where point C and D are symmetrical to each other. This resistance R, which is between points A and C, that is branch AC, is symmetrical with branch AD, and branch CB is symmetrical with branch DB. Now, if we fold this circuit along the line AB, then the upper half of the circuit coincides completely with the lower half of the circuit. So, this type of symmetry is called folding symmetry. Now, in case of folding symmetry, the symmetrical point, that is point C and D, will have same potential. Let us take this potential to be X. So point C and D will have same potential, which we have taken as X. Now, these two resistor of value R by 2, which was actually a resistor of value R, is connected between point C and D, and there is no potential difference between C and D. So, this resistor is ineffective. Now, this circuit becomes like this, and if we take the potential of point A as VA and potential of point B as VB, then we can see that the resistor connected between point A and C and the resistor connected between point A and D has equal potential difference, which is VA minus X. So these two resistors can be considered as are in parallel combination, and their effective resistance will be R by 2. And similarly, the resistor in branch CB and branch DB, which are also of value R, they are also equal potential difference between their ends, that is X minus VB. So these resistors also are in parallel combination, and their effective resistance will also be R by 2. So the circuit now changes like this, where there are two resistors, each of value R by 2, which are connected in series between A and B. So the equivalent resistance between A and B is R. Since two resistors, each of value R by 2 in series combination gives us equivalent resistance R. Let us consider another example. Find the equivalent resistance between point A and D for the given circuit. Here a circuit is given, and we have to calculate the equivalent resistance between points A and D. So first we will check if this circuit has folding symmetry. So we draw a line through A and D and check for the folding symmetry of this circuit. If we fold the circuit along line AD, this circuit clearly coincides with the lower half of the circuit. So this circuit has folding symmetry. Therefore, point B and point F must have equal potential, and similarly point C and point E will have equal potential. Let us take this potential as X and Y. So potential of point B is X and point F is also X. Potential of point C is Y and potential of point E is also Y. Let us assign potential of point A as VA, potential of point O as VO, and potential of point D as VD. Now we can see that resistor in arm AB, which is of value R, and resistor in arm AF, which is also of value R, are connected between two points which have equal potential difference. That is, point A and B has potential difference VA minus X, and that is also true for point A and F, which has also potential difference VA minus X. So these two resistors can be considered as in parallel combination. So their effective resistance will be R by 2. That is, we may ignore this resistor R in the lower half of the circuit and make the resistor R in the upper half of the circuit as R by 2. Similarly, the resistor in the branch BO and resistor in the branch FO also have equal potential difference. So these two resistors can be treated as in parallel combination. So their equivalent resistance will be R by 2. So we may ignore the resistor R in the lower half and make the resistor R in the upper half R by 2 of value R by 2. This is also true for these two resistors which are connected between FE and BC. We can ignore the resistor between FE and make the resistor between BC as R by 2. And applying the same process, all the resistor in the upper half will be of value R by 2 and all the resistor in the lower half can be neglected. So the circuit becomes like this, where there are two resistors which are of value R by 2 in series, and their equivalent resistance will be R by 2 plus R by 2, that is equal to R. Now this resistor will be in parallel with this R by 2 resistor, or the circuit becomes like this, where there are two resistors, one of value R by 2 and one of value R in parallel combination between B and C. Now these two resistors are in parallel combination, so their effective resistance will be R by 3, and this circuit becomes as series combination of three resistors having value R by 2, R by 3 and R by 2. So their effective resistance between point A and D will be R by 2 plus R by 3 plus R by 2, which is equal to 4R by 3. Find the equivalent resistance between point A and D for the given circuit. So at first we will check if the circuit has folding symmetry about the line AD. So we first draw a line through A and D, and we can see that the circuit has folding symmetry about this line, where if we fold the circuit about this line, point B coincides with point C, and this resistance R coincides with this resistance R. This is true for these two resistors, and point E coincides with point F. and this resistance 2R coincides with this resistance 2R. So this circuit has folding symmetry about the line through AD. So point B and point C will have the same potential. We write this potential as X, and point E and F will have same potential. We write this potential as Y. Now we can see that the resistor R, which is connected between E and F, has no potential difference across its two ends. So these resistors can be ignored from the circuit. Same is the case for the resistor which is connected between B and C. This resistor also have zero potential difference between its ends. So this resistor can also be ignored from the circuit. And if the potential of point A is taken at VA, we can see that this resistor R is connected between A and B, has a potential difference VA minus X, and this resistor R, which is connected between A and C, also has potential difference VA minus X between its end. So these two resistors can be considered as are in parallel combination. So their equivalent resistance will be R by 2. So we can ignore one resistor and take the other as R by 2. Similar is the case for the resistor connected between point D and E and point D and F. Both resistors has equal potential difference between their ends. So these two resistors can also be treated as a parallel combination, and we can ignore one resistor and make the other as R by 2. Since effective resistance of a parallel combination of two resistors each of value R gives R by 2. And these two resistors which are connected between point B and E and C and F also has equal potential difference between their ends. So these two resistors can also be considered as are in parallel combination, so their effective resistance gives us R. And we can ignore one resistor and make the other of value R. Now this circuit reduces to this circuit where between A and D there is a resistor, where between A and D there is a resistor of value 2R, one of value R by 2, between A and C, and one of value R between F and C, and one of value R by 2 between D and F. Now these three resistors of value R by 2, R and R by 2 are in series combination, so their effective resistance will be R by 2 plus R by 2, that is equal to 2R. So the equivalent resistance reduces to this, where there are two resistors between A and D, each of value 2R, and these are connected in parallel combination. These are in parallel combination. So effective resistance between A and D will be R. So in case of folding symmetry of a circuit, we can just ignore one half of the circuit and make all the resistor of the other half of its initial value. As for example, for the given circuit, we ignore the lower half of the circuit and here make each resistor of value R by 2. And if we simplify the circuit, we get the equivalent resistance between A and D.